was ready.
All right, today we're going to finish up the course with real-time systems. So far, let's see. We've so far talked about mainly general-purpose systems, although we've talked about somewhat in supercomputing. Real-time systems are going to have a different requirement where certain operations must complete within a deadline or very, very bad things occur. And so your operating system is going to be a little different. Can anyone guess what the differences might be?
It's going to have a clock.
It'll have a clock. So does every other system, but sure. Has a clock, yeah. What do you think the size of a real-time system is versus a server operating system? Small. Yeah, a lot of times real-time systems are going to be very small, and they're also going to be very, very specific. All right, we'll go over certain characteristics, and we'll talk about timing. Big thing here is hard versus soft. What are the timing requirements, and scheduling as well are the big things here. Now, before I continue, I'm actually sad about how short this chapter is, because I could do an entire semester on real-time systems and still not cover everything, and we could do like a cool little physical object of doing something. I had one time where we had a little arm that went back and forth, and the real-time system was to make it light up certain messages, so as it went back and forth real fast you could actually see it light up some words, and then make it also scroll maybe at the same time. And there's plenty of other real-time applications we can do. But we're just going to do
independent study.
We could do that for an independent study. Oh yeah, I need to talk to you about that as well. All right. So, quick overview. Real time just needs results produced within a specific timeline. If you're doing word processing, usually you don't have a deadline that you have to, when you hit the key, when it needs to show up. Obviously, you don't want to be impatient, but it's not like if the key or character doesn't show up, someone dies or something bad happens. So that's not a real-time system. Embedded, usually it's an embedded system. For example, in your automobile, the computer that's computing, the fuel-air ratio is real-time because it needs to calculate what that is before the deadline of the next time it needs to, utilize the injector. Safety critical systems could have catastrophic results. If you're a pacemaker, you probably need to make sure it's beating at the proper time.
Probably.
By that I mean definitely.
Most likely.
Most likely. Definitely. We're going with definitely, okay? All right. Also, there's real hard time systems, guarantees it to be completed, and soft provides some type of priority to the tasks. Most of the time we're concerned about real hard time or hard real-time systems. Soft are useful when you might have spikes that you have to deal with, and then you might be able to guarantee it to go back to like a hard real-time system situation. Most of the time we're going to look at the hard real-time systems because that's what we work with most of the time. All right, single purpose. For example, automotive, it's only there to compute what the next air-fuel ratio is. That's all it does. Very special purpose, very small. Usually very inexpensively to mass produce. Now, to create one of them can be somewhat expensive, but usually when you mass produce it, it's very small, and then you're going to have very specific timing requirements. These are 4 common characteristics. Now, it doesn't necessarily have to be small size or single purpose or inexpensive, but you pretty much always have specific timing requirements. The top 3 are just normally what you encounter. Yeah, we'll talk about that in 1 minute. I meant to skip that. So in a bus-oriented system, and this is what we've been talking about the entire time, you might have your CPU, which communicates over a bus to disk controllers, maybe a USB controller to all your peripherals, and of course a monitor as well as main memory. What's this disadvantage of this structure?
The CPU is talking to a graphics adapter, nobody else can talk.
Right, and then, so therefore it's a bad thing. It's performance issues. And you're doing the circle, so what's the circle problem?
That's all I got.
That's all you got? All right. And this is how most of our systems are built. But as you hopefully pointed out, there could be some performance issues. The way they get around that is instead of having all these different peripherals tied to a bus, they do something called system on a chip, where they essentially put everything on one chip. And this is very common to do for an embedded real-time system. So your CPU, your memory management unit, and a lot of attached peripherals like your USB ports are all in one circuit or one chip. And that, therefore, you can do a lot of performance hardware-wise because you don't have to communicate off the chip and then back on. So this is actually very common in a real-time system. So that's your first performance boost. Now, what's a downfall here of doing system on a chip?
Space.
Space. How much memory do you think it has?
Not a lot.
Not a lot.
And technically, you probably couldn't add more to it.
And yeah, there's the other problem. You're not going to be able to add to it. It's very specialized is the deal. But by making it more specialized, you have better performance.
Sure.
Yes?
Yeah.
In general. All right, we did bus. All right, kernels. Most real-time systems don't provide features found in standard desktop. That's true. Reasons include, well, let's not go into that. Let's actually do examples. For example, virtual memory. A lot of real-time systems do not implement virtual memory. Why is that? Well, if you have virtual memory, you have to go to a TLB, which may make your memory references have a varying latency. But if you don't have virtual memory and you're always reaching out to main memory, then you can actually tie down what the exact timing requirements are. One thing I haven't mentioned is in a real-time system, you're always looking at the worst case scenario. You don't actually care about the average case, which is what we care about in servers, because we want to know on average how much can we service. In real time, you want to know what's the worst case, because you want to be able to calculate the fuel-air ratio. You want to be able to calculate or make sure that heart is still beating. All right, real-time addressing. CPU creates the actual address. Relocation. Actually, the picture makes more sense here. CPU produces the memory location. The first one, it doesn't do any computation, goes straight to physical memory and brings it back. Since this is on chip, hopefully it's faster. Relocation register, it just adds R. And the one down here is the page table with the TLB, which is what we've talked about in a previous chapter, where you use your TLB to hopefully cache where you need to jump to in main memory. So which of these, I've already said it, but which of these are usually used? Or do you believe? Which one are usually used in real-time systems?
The top two.
The top two are usually used. The bottom one is usually too slow. There are a couple out there that use it, but in general, it's too slow. Or it's not so much too slow as it's not predictable enough. In real-time systems, you want it to be predictable. That's what you want the most. Okay. So we talked a little bit of features of real-time systems. We're going to say it must provide three things: preemptive, priority-based scheduling. What does that mean?
More important stuff that come first.
Right, and why would we want that?
So people don't die.
So people don't die. If you need to compute something quickly from an event, you need to be preemptive. Now, how's that different than a preemptive kernel?
It needs to know what it's going to do next too.
Okay, sure. It needs to know what it's going to do next. The top one is user space programs. The second one is kernel space programs. You can preempt the user programs. You can preempt the kernel. Why do we need to also preempt the kernel?
So it doesn't have to figure out what to do
So it doesn't have to figure out what to do.
and waste time.
Because if the kernel program isn't a high priority, then the user space program, which is a high priority, must take precedent.
Right, okay. If the kernel's currently doing a low priority task and a high priority comes in, you need to be able to stop the kernel and move over. Right. And number three? Right. We need to service these things as fast as possible. Okay. How do we go about minimizing latency? All right, latency is the amount of time from when an event occurs to when it is finished being serviced. Simple definition. We're all good there? No? What do you need?
I need like flowcharts.
You need a flow chart? You want like a Gantt chart and maybe some Venn diagrams?
Yeah, Venn diagrams.
Venn diagrams? Okay. I'll keep that in mind for
UML.
next time.
Yeah.
UML. Okay.
I'll put that in my review of you.
Okay, good. Thanks. All right. So latency, this is the total latency. It's going to be cut up into about 3 different categories: interrupt, dispatch, and then actual execution. So first is the interrupt, because some other task is running when the interrupt comes in. So it needs to be able to stop the task, the interrupt type. There's a time for when the CPU gets interrupted. Figure out what the interrupt type is, do the full context switch, and then you can start your ISR, which should be your interrupt service routine.
Yes.
So this is your interrupt latency. So that's the first thing that must happen. Next comes dispatch, amount of time required for the scheduler to stop one process and start another. Because the interrupt is determine the type and then do a context switch, usually with the scheduler. Then the scheduler has to stop the process completely and then start the other process. So that's the whole, figure out all the conflicts and then dispatch the proper process to start running. And then you can actually execute it. Execute the routine. Now hopefully this over here is what's taking up most of the time, but not always.
That's not what this graph shows.
Definitely not what this graph shows, which unfortunately can be the case. All right, everyone understand the latency?
Mm-hmm.
All right, we're just gonna
Latency bad.
high latency bad, low latency good. All right. You all know that from games.
Latency,
Then you are
good,
breaking the laws of physics.
which would be super good.
Yeah, maybe. I don't know. What would the world be like?
Let's find out.
And if you can break them, are they really laws?
They're more like
Exactly.
guidelines.
Exactly, because a law describes what's going on. I mean, what it is, not what's going on, but what it is. So, yeah.
Whereas a theory is what we think it is.
Or theory explains why or how it occurs. Yeah, something like that. It's been a while since I've looked at the definition between the two. Our real-time scheduling. Hopefully you can see that, well, in certain very specific devices like an automotive one where it may only be computing, air-fuel ratio. Hopefully that's its only task and you're good to go. But you may have a system that has to do a lot of different processes. For like in airlines is actually a very common example because it needs to calculate a bunch of different features of the plane at the same time. So we need to figure out how do we prioritize, because moving the rudder is probably more important than playing the video on the screens.
If the plane's going to crash either way, then might as well die.
Okay. Thank you, Matt. Do me a favor. Don't work for Boeing. All right. Good. Good talk. Good talk. All right. So periodic processes require specified intervals. If your process comes in at different periods, that's actually very nice. So you just need to know when it comes in, and then the deadline after it comes, it arrives might be D, and then the T is the processing time. So if you know it comes in every P interval, it takes this much time, hopefully you can schedule it before the deadline occurs.
What if you can't?
Right. Well, we're getting there. This would be great if you know the exact time every process comes in, how long it takes, or when the deadline is, and you know how long the process takes for everything. Then you could probably set a very static scheduler and just let it run. This is not always the case, but we wanted to start here to show you, hey, look, if you do know all this information, you can just statically schedule it and we're good to go.
Just like the pacemaker.
Yeah, exactly, like the pacemaker. Airline a little different because you're waiting, or airplane a little different because you're waiting on events. So if you're waiting on an event to occur, then maybe you'll have a priority. So maybe P2 has, for example, you have P1 and P2, and P2 has a higher priority. It needs to be done. It's more important that its deadline is completed before P1. And now if you do it just straight by priority, here's an example where P1's deadline is here, and then the second run of P1 and the first run of P2 is due here. But by executing process 2 first, P1 does not meet its deadline, where if you just swap the two, they both would have met their deadline.
Sure.
Right? So we're just talking about how it may not, highest priority first is not necessarily the best algorithm for real-time systems, is what this slide's trying to tell you. The book goes through 2 different ways to do scheduling in a real-time system. The first is rate monotonic, where you don't assign a priority. Well, the scheduler assigns a priority by the periods of the how long the program takes to complete. So, in order to do this scheduling, you need to know how long a process takes to complete for this one. So if the shortest one has higher priority, the longer ones have lower priority. Therefore, P1 would be assigned a higher priority of P2, because if you look back here, P1 took less time than P2.
So if you keep getting shorter ones, do they go in front?
Yes.
So it can starve.
It can starve something else, that's correct. But in general, the reason why this is usually okay is that you may have P1 and it's based on some event. Well, that event may not happen for a while. So the reason why the rate monotonic usually works is because the events come, you can predict the events to some degree of when they're going to occur. So you're not going to just be flooded with a bunch of events. There's also usually a throttling with the events at some point, or maybe not allowing all of them to go through at the same time. So this is what you're talking about is something more on a server side that would occur, because you might have a flood of requests. But here, your events are usually a little more predictable.
Cool.
So deadline for P1 also happens to be the next time the P1 event occurs. So notice that since P1 is shorter, you do P1 first, you start P2, then P1 comes in again. Since he's shorter, he interrupts P2, executes, and then P2 begins. But in this case, they both actually complete within their deadline. Even though P2 is being split up in this situation, it's still perfectly fine. All right. We're good so far?
In this example, since process 2 actually has, once it's split, has less time than P1, is there a different type that would just let P2 finish because P1 will still finish before its next deadline?
Oh, you mean have P2 finish here before P1 begins?
Right.
So that would be what is it? Shortest time left would be the one you're thinking of. And that would be that's a version of rate monotonic. So when it got here, it would realize P2 only has this sliver left, it would let it complete, and then would find out who's next, who has the next amount of time. And that's a version of rate monotonic. Okay. Does it tell you about the error or the problem here? Yes. So, what might happen with rate monotonic is that if your deadlines were a little different, notice that back here, P1 and P2, basically P2's deadline was after 2 P1s. But we'll say, for example, P2's deadline is moved up just a little more. And this is what you were talking about, where maybe this deadline P2 needs to come up. So in this case, the rate monotonic would fail to schedule this properly. Right. You could do the shortest deadline first, or actually I said that wrong. It's earliest, what I talked about is shortest time left, which is a version of rate monotonic. The other version that they come up is earliest deadline first. So the caveat I told you is shortest period left. So how much is left to execute. This one is who has the earliest deadline, execute them next. So the earlier deadline has a priority, obviously P1. He's got the next priority, or next deadline, let him go. Start P2, because he has the next priority. Even though P1 came in here, P2's next, so you keep executing P2. And then that is how it flips back and forth. Notice here, the priority is relative to the deadline, not the period. Excuse me? So you need to know the deadline ahead of time. And this is the big difference here. With earliest deadline first, you need to know the deadline. With rate monotonic, you need to know how long a process takes to complete. So if you only know one of those pieces of information, you can choose one of these two schedulers. what? Proportional sharing scheduling? Yeah, so you have a bunch of shares. An application has so many shares, will not receive more than a total number of the processor time. So, yeah, this is the communist solution. I actually haven't seen this done too often.
Because communism doesn't work.
Right.
Despite all the pamphlets.
It works on paper, man.
That's why it's on
I said,
pamphlets.
despite all the pamphlets.
All right, pthreads, you can actually force this to either first come, first serve. I don't know why the book included this. First come, first serve, or round robin, which isn't anything like what we just talked about. Oh, and then they go into VxWorks, which is another type of operating system for real time, but I don't really care about that, nor do I care about the Win microkernel, and that's the end of the chapter.
Woo!
That was beautiful, man.
I
Thank you.
forgot to put the confetti on the roof with the screen.
Any
I was
questions
busy looking
about
at
real-time systems? Told you this would be short.
Do you ever combine those scheduling systems?
Do I combine the scheduling
For
systems?
any weird reason you
Oh.
want to?
So what you could do if you knew both is you could come up with a like a two-level scheduler where you would get the answer from rate monotonic and earliest deadline first, and then you'd have some type of maybe tournament or not tournament predictor, but a
No, that sounds good.
tournament predictor about who is more correct, and then you would just choose that response and move on. Yeah, we could do that. How about that? Did you like that one? I have no idea if anyone does it. I just thought of that off the top of my head.
You should go make millions of dollars. You're welcome.
No other questions? All right. Oh, yes?
Yeah, I got a question. So, do those things, the little things that they run on, are they completely isolated, or do they communicate with other ones, or?
Usually you want them to be isolated. You want to minimize communication
So
because
like
that's
an
unpredictable.
airplane would have like one.
An airplane would probably have 4, or the latest Boeing one, I think it was either the 777 or 787, has 4 of these things, and each one of them can do all the necessary operations of the airplane that are for it to not
So
crash.
it's just for redundancy? Or?
Well, the way they did it is they had 4 for redundancy, and then if all 4 are running, you get your video and everything else. If only,
So
I think
one of
actually if
them-
only 3 are running, you still get all your capabilities.
So if 3 of them are running, does each one just work on a specific task? Or?
I would assume so. Boeing is a little, they're not going to tell you everything that's going on, but I would assume that they would load balance it amongst the 4 because it's a way to test that it's still operating, right? And then if you're done, I remember if you're down to 2, you lose your video, you lose your power and sound, but you still have a pressurized cabin, and you can fly.
I don't know, I think I'd take the video over that.
A pressurized cabin? Better descend quickly.
Never work at Boeing.
Never work at Boeing. All right.